Oh, yeah. Graph your right here. Okay, 6.2. All right, so we're going to do volumes now. We did areas last time. We're going to do volumes now. Now we're going to do volumes in 6.2, 6.3, and 6.4. So it's largely a volumes chapter. All right. So 6.2, volumes of solids. Volumes of solids. Now, not quite like that TV set. That TV set is more like Calc 3, all right? So we're going to do this kind of thing. We're going to take a plane region and revolve it about an axis. That's called the solid of revolution. Volumes of solids of revolution. Okay, so that's 6.2 and 6.3 actually. 6.2 and 6.3 in fact. 6.3 also. Okay, we do it one way in 6.2, another way in 6.3. And in 6.4 we deal with volumes of shapes and solids that are a bit more general. Okay, not quite like him, but all right. So what we're going to do today, we're going to do the disc and washer method today. All right. All right. Starting with the disc method. All right. So I'll start with an example. And this is best seen by example. To be very blunt, it's not the kind of chapter where you want to stare at the formulas in Stokowski, or even my notes, in terms of generic formulas. It's a matter of knowing your basic geometry formulas and knowing how to integrate them into the integration. All right. So, sketch the region R. We'll often use R to represent the region. Okay. Now, R is going to be a plane region, meaning it's a region that lives in a plane. SpongeBob SquarePants? Okay, lives in the plane. All right. Okay, we're going to take this region, revolve it. Okay, sketch the region R bounded by. Okay, so you're going to be given equations for the graphs that form the boundaries of the region. You might have only one equation, like it might be a circle, for example. All right, but it usually involves more than one equation. All right, bounded by the graphs of y equals x squared. The x-axis, that's pretty common, the x-axis, x equals 1 and x equals 3. All right. The idea is that if you draw the graphs here, okay, they're going to determine one region of bounded area, okay. So you're going to take that guy, that plane region, we're going to revolve him around. Okay. Well, what do we revolve it around? Find the volume. All right, this is the last time I'm going to handwrite these words. All right, find the volume of the solid generated. Okay, that goes without saying. Find the volume of the solid that's generated, that's created. If R, this plane region, is revolved about, and then this is all right. If R, that plane region, is revolved about, and as you can imagine, this is very important. Okay, what is the axis of revolution? Let's say it is the x-axis. In a way, that's the most basic case, about the x-axis. And from now on, just to speed things up in the lecture, I might just do it like this. Here's the x-axis. I'll show this twirly thing. It means that we're going to take the plane region revolved about the x-axis. So I might use that as a shorthand, okay? Instead of having to write all this out. Okay. Not that I'm anti-sentence, it's just that we want to get on with it. All right. All right. Okay, first of all, now, very often I will ask you to sketch the region. Not always. I mean, there are some cases where you don't have to sketch it, but often I do ask you to sketch the region, meaning that I would like the intersection points. And actually, I would like more information than what's in my notes. Okay, so sketch your region. And let's do the full-blown job here, and let's indicate the key intersection points as well. So my notes, I do sketch it out, but I don't put as many points in as maybe I should. Okay, to clearly indicate what the region is. All right, x-axis, y-axis. All right. Okay, the graph of y equals x squared. We know him, right? He's a parabola opening up. But we only care what's happening between x equals 1 and x equals 3. They're like brick walls, right? Okay. So here's a piece of that parabola, right? Y equals x squared. All right. Here's x equals 1. Instead of writing x equals 1, I might just do this. and the x-axis. All right. So clearly, the bounded region we care about is this here, obviously. Okay, and I'll label that with an R. All right. So that's the plane region of interest. In 6.1, we might ask for the area, and of course that's fair. It's very easy here. All right. But now we're going to take this plane region and we're going to revolve it about, we're going to say the x-axis. Okay. Now, you don't always have to do this, but if you try to visualize this, what does it kind of look like? Well, looks like a bullhorn maybe. It looks like a solid bullhorn or something, right? Okay, maybe something like that. Okay. In count 3, you'll be doing more three-dimensional pictures, not so much here. Okay, maybe a little bit. All right. So here I'm sketching the solid. In a way, it's my step 2, sort of sketching the solid. Although in this class, that's typically optional. In your Calc 3 class, you may well be required to do that. Okay. But here I just sketch the solid. The axis goes through like this. Right. But sketching the solid usually isn't the big thing in this class. All right. Third. All right. Let's see. Now here's the deal. When we do this, it's like we're taking a slicer, okay, and we're looking at cross sections of this solid. What happens if we slice this thing up? All right. So let's find the area of a cross section we get. Find the area of a cross section. Okay. All right. So specifically, we're going to find the area of a cross section at x. Okay. Where x is in the closed interval from 1 to 3. Okay, so kind of a long statement here, but find the area of a cross section at x, where x is some arbitrary value between 1 and 3. Now bear in mind, if something really changes between 1 and 3, then you're going to want to split up the interval anyway, right? Okay, but it looks like we have a very consistent situation going from 1 to 3. It looks like our Xerox scanner will apply the same rules as we go from 1 to 3, right? So we take some arbitrary x in there, and that's a good technique, right? And we consider the corresponding cross-section. So we take this slicer, right, and we slice this thing at x, okay, we get this line segment, all right? And if we revolve it around, what do we get? You get a circular disc. Now I know that, if this is two-dimensional, it's kind of hard to see it. It's like there's a record, like a solid record you're putting in here, right? So you have this disc here that's going into the board. All right. Of course, we're drawing on a two-dimensional thing. All right. So we want to know the cross-section at x, all right? So it's that guy over there, all right? Okay, well, let's talk about this guy. All right. So here's the cross-section at x. Maybe I'll draw, don't like this, yeah. Okay, so it's like we take out this record, but it's a record with no hole in it, right? Okay, so we take this record out, this disc, all right, and we lay it down flat. Now, I'm going to call this a thin disc. Like a thin mint, almost a thin disc. All right, because he has infinitesimal thickness, right? Infinitesimal thickness. That's kind of what the dx is. Infinitesimal thickness. All right. Now, what is the area of this thing? All right. Well, the cross section here is a disc. All right. We get a disc. Okay. With area what? Okay. With area what? Well, come on. We have a circle. I hope you remember this. What is the formula for the area of a circle of radius r squared? Radius r. Now, I kind of hesitated when I said r. Bear in mind that we're going to use r as a constant later on in the chapter. I'm going to write this generically as pi times radius squared. Okay. I want to write that down because I want to make it clear that, or you could write r of x if you wish. You could also write this as r of x. Bear in mind the radius changes with x. Okay, as we go from x equals 1 to x equals 3, the radius is going to get bigger. Right? And what gives us this radius? Okay, so what is the radius of this disk? All right. Well, take a look here. We have this. Okay, we have this point here, this point here. All right. Now I'm going to move some of these ideas earlier. Some of the later ideas earlier on. Okay. Pi times radius squared. So what is the radius? It's going to be the y-coordinate on top in terms of x, minus the y-coordinate on the bottom in terms of x. All right. For good measure, you could put of x of x. this x, the y coordinate here is given by what? F of x or x squared in this case. Right. Okay, so it's given by f of x or x squared in this case. All right, minus, well, over here, the bottom of this radius, this physical radius, yeah, what's the y coordinate here on the x-axis? It's 0. Okay, so top minus bottom, you have that theme again, right? Top minus bottom. X squared minus 0, that's x squared. All right. Again, I mentioned this idea of top minus bottom later on in this section, but I may as well talk about it now, so that we make some things clear. And like I said, even in my notes, when I write f of x and g of x, you know, that's not the way to think about these things. F of x and g of x. Just do it, you know, with the formulas you know from before, from geometry, and use your head. Okay, be careful. All right. So equals pi times. We agree the radius is x squared, meaning that, you know, if we take any value for x between 1 and 3, the radius is given by x squared. So if x is 2, we get 4. If x is 2.5, we get 6.25, and so forth. All right. Pi times x squared squared. What's the square of x squared? X squared. So we get pi x to the 4th. I'll circle that. All right. So for example, when x is 1, okay, so the radius is 1 squared or 1, but the area is going to be pi times 1. That's pi. So the radius here is pi. The radius here is going to be, wow, 81 pi over here. Okay. Sorry, the area, yeah, the area here of the cross section of the disk is 81 pi. And if these are in meters, then that would be square meters.
Where do we get the top and y bottom from?
Yeah, okay, well, okay, now, first of all, remember that a radius can never be negative. Okay, and if it's 0, you just have a dot. Okay, but the radius can never be negative, which means that when you work through the problems in this chapter, you're always thinking top minus bottom. So in terms of y coordinates, you're thinking top minus bottom, so that the result is not negative. If you're talking about a change in x coordinates, it's what? Right minus left. Okay, to make sure the result is not negative. The radius cannot be negative.
The only time the bottom is going to not be 0 is if like the graph is shifted or if you're using another graph, or?
Well, in this kind of example, it's where we shift the axis of revolution. For example, what if, and we're going to talk about this later with the weird axes, what if the axis of revolution is y equals negative 2? Then it's going to be x squared minus negative 2, or x squared plus 2. So basically, this guy here might not be a 0 if we're changing the axis of revolution. And we're going to do that later. Okay. Right now, we're just keeping it to the regular coordinate axes. And you're right, one of these would be 0.
So you're saying that the x-axis and the axis of revolution may be different?
Oh, yeah. See, as part of this problem, in a standard problem, I will give you what the axis of revolution is, and it really matters. Okay? In our most basic example, the x-axis is the axis of revolution. But later on, we'll use the y-axis. Later on, we'll use y equals negative 2. But in my class, at least, it will always be horizontal or vertical. I'm not going to give you a diagonal. Okay. And later on, I'm going to have you find the volume of a sphere, in which case you can choose what to do. Model it yourself. With the sphere, we'll talk about that. Okay. Anything else? That's a formula. That's a formula that describes the cross-sectional areas as we go from x equals 1 to x equals 3. Any questions? Any questions? Now, let's see, that's step 3, okay, and then step 4. Let's actually integrate. All right. Notice that I have not done any calculus yet, okay, but now we're going to integrate. We're going to integrate the cross-sectional areas. Integrate the cross-sectional areas, okay, to get the volume. Okay. Bear in mind, on the chapter 6 test, if I tell you to just set up the integral, once you set up an integral with all the details, then you don't have to work it and get the actual volume. Of course, in other problems, you do have to find the volume. All right. But integrate the cross-sectional areas to get the volume. So it's like they give a scanner, all right? Remember how before, okay, in 6.1, what do? To find the area of the region, we integrated the lengths of the line segments, right? Okay, the heights of these things, all right? But now, to find the volume, we integrate areas, okay? So basically, we integrate a lower dimensional measure to get a higher dimensional measure, all right? So we integrate areas to get volumes. And that's basically the idea. Okay, so let's do this. So B equals, all right. By the way, questions, any other questions? Any other questions? We're going to do the calculus now, all right? If anything, this is the easy part. Now, here, we're doing a dx scan, all right? And, sometimes you're going to do a dx scan, other times you're going to do a dy scan, all right? Now, why are we using a dx scan here? Well, the reason is very straightforward. It's because we're evolving about a horizontal axis, all right? If you're evolving around a horizontal axis, then if you're evolving around a horizontal axis, and if I tell you that you have to use the disk method, okay, or if the disk method is one of the options I'm giving you, okay, then you have to do a dx scan, not a dy scan. So on a disk method problem, all right, if you know the axis of revolution, that forces whether it's a dx scan or a dy scan. Now on the exam, you might get a choice, okay, from very different methods, all right. For example, in 6.3, we're going to ask, well, how do you do this using a dy scan, all right? But in 6.2, we're going to say, hey, if it's the x-axis, it's dx. If it's any horizontal axis, for an axis of revolution, it's going to be dx, all right? And there's a way of seeing that, right? Because how do we do a dx scan for this region, as we did in 6.1? It's like the Xerox scanner, right? Okay, so it's like a scanner goes like this, 1, and so forth, 2, 2.2, 2.5, etc., over to 3. So we're scanning like this, all right? Okay, so if I do these, toothpicks, and I find these toothpicks to be helpful, right? You can just draw a few of them. But if I take any one of these toothpicks and revolve it around, I get a disc. You might ask, well, what happens if we do it the dy way? Well, we're going to talk about that in 6.3. You can think about it. Okay, but these toothpicks rotate around, they revolve around, we get a disc. And I'm using these thin discs that are infinitesimally thin. How are we scanning? We're scanning from x equals what to x equals what? X equals 1, x equals 3. Right? And of course, in the initial setup, the lesser number is the lower limit, the greater number is the upper limit. That may change if you do a u sub later. Okay, now, once again, hey, well, what is it that we're integrating? These cross-sectional areas. We found it. Pi times radius squared, pi x to the 4th. Okay? All right. And then let's go on. All right. The pi can pop out. All right. Integrate x to the 4th.
X to the 5th over 5.
X to the 5th over 5. We're going from 1 to 3. You should be able to do this, right? Pi times, I'm kind of reviewing chapter 5. You plug in the 3. Plug in the 1. Okay, I don't need extra grouping symbols here. We just have one term over here. Okay, this turns out to be what? Turns out to be it's not that nice. 242 pi over 5. 242 pi over 5. Okay, and by the way, if the original distances were in meters, this would be in what? If it's volume, it's what? Yeah, cubic meters. Yeah. All right. And for the first time in this chapter, we see pi here because there's this revolving going around, right? We didn't have that back in 6.1. So we have pi here, almost, maybe for the first time. I forgot if there was a trig guy we did earlier. Okay, 2.2 pi over 5 cubic meters. All right, and that is the volume of that solid concrete bullhorn. You can't blow through it; it's solid. Questions? Questions? Okay, you integrate these heights to get areas. You integrate areas to get volumes. That's the basic idea. Any questions? This idea of scanning areas to get volumes, that's kind of informal. Very briefly, I want to relate this to the Riemann theory, right? So what's the theory behind this? Just to convince you that we do in fact have an integral, all right? So what's the basic idea? This region that we're dealing with, all right? One way you can develop this from pre-calculus is, okay, what if we start with a Riemann approximation? What if we start off with a bunch of rectangles, right? Rectangle, rectangle, rectangle. Okay, kind of chunky there, but okay. So we start off with these rectangles, okay? Now, if I take one of these rectangles and I revolve him, okay, I'm going to get a hockey puck. All right, I get a hockey puck. And actually, you know what, ladies and gentlemen? Okay, that is technically a disk, okay? Where the thickness is like delta x, assume it's a regular partition. So the idea is that we get a disk, a bona fide disk, all right, with thickness delta x. All right, we get a disk with thickness delta x. Technically, that's a disk. When we talk about the disk method, that's actually a disk. Those guys I was talking about earlier, they're like thin mints. They're infinitesimally thin disks. Technically, a disk has some thickness. All right. Now, you agree that we can approximate the volume of that bullhorn by taking the 3 hockey pucks we get, right, and adding up the volumes, right? Then we get an approximation. And then what do? We consider various partitions from 1 to 3, right? And we let the norms of these partitions approach 0. Make them finer and finer. If this is continuous, then we're going to get an exact value down the line. So you can see here how this leads to an integral, right? Because the idea is that the limit, okay, as the norms approach 0, okay, of the sum of these disk volumes, okay, the sum of these disk volumes, all right, that's going to give us an integral. The integral from a to b of, such and such dx. All right? And by the way, the delta x here does eventually become dx. Okay? The delta x becomes dx. And that's why it is that when you look at the Riemann sum, right, it's like you have an area times delta x, right? It's like the area of this face of the hockey puck times delta x, all right? We're picking up the face of that hockey puck in that integram, all right? And as it gets finer and finer, it doesn't matter if it's right or left or midpoint or whatever. Okay, but the idea is that the area is like square meters, and then the delta x throws in a times another meters, right? Okay, which is why when we integrate with respect to x here, we raise it another dimension, and we go from square meters to cubic meters, because the delta x brings in another meters unit, right? When you multiply this is in cubic meters. And when you add things up, you retain the unit, it's still cubic meters. Okay, and in the integral, it's still cubic meters. Okay. So the dx indicates that you're bumping up the dimension, and it used to be delta x. Right, that's width. Right. But any questions? I'm trying to explain why it is an integral is appropriate. Okay. It's a similar decomposition of the region, but we're considering these hockey pucks, not just rectangles. And these are technically the disks. Okay, I use thin disks for the integram, but these are technically the disks. Questions? Questions? That's the theory. Right. You can see the notation in full glory in the textbook. All right. Okay. So I have some generic comments in the notes. Fair enough. One comment. Okay, I'll just recite this orally. Even if this guy is below the x-axis, what if this is y equals the opposite of x squared, and he's down here, all right? Now, what happens is that the radius, okay, the radius is obtained by going 0 minus this guy, all right? But still, it's going to be x squared, all right? So the idea is that if you go top minus bottom, your result will not be negative, okay? And in fact, some of you might go, well, wait a minute, does the sign really matter, right? I mean, here's the deal. It goes pi radius squared, right? So does the square really care? In that sense, you have some flexibility. Like, for example, if you had y equals negative x squared down here, and you did something similar, then you can plug in negative x squared directly, and it will work. But the thing is, you're really relying on that square, though, in pi radius squared. So just to be safe, I think it's best to think in terms of top minus bottom. So I do know that in my note here, I mentioned that you don't have to worry too much about signs. But if you do things top minus bottom, right minus left, then you're not going to get anything negative anyway. So you'll be okay.
Yeah, so you're saying that it doesn't matter because it'll be like 0 minus minus.
Yeah. Again, if you do top minus bottom, right, what's going to happen is here's y equals 0, right? X-axis y equals 0, right? Okay. And let's say this y equals negative x squared. Okay. Well, 0 minus negative x squared is still x squared. Okay, that is the radius, and that's not negative. Okay. Now, they mentioned it, Swakowski, and in my note here, at the bottom of page 2 of my notes for this section, I mentioned you could plug this in directly because of the fact that if you have pi radius squared, that square doesn't care so much, but you know what? Later on, squares aren't going to save you. So, generally speaking, I think it's safest to go top minus bottom. Even though, as Rakowski mentioned, you know what, since the square doesn't care, we can get away with more, but still, that's a little sloppy, technically. So it is good to put in the actual radius in, okay, for pi radius squared, okay, where the radius is non-negative. I think that's good form, just in general. All right. Still, there is some flexibility in making a mistake with signs, but you shouldn't have to rely on that. All right. But any questions on the example, sort of how the theory builds things up? We get an integral. When you take a limit of Riemann sums, you get an integral. Right? When you take the limit of these kinds of Riemann sums, you get an integral. Questions? Questions? Let's do. Whoa! Before we do that, and we'll mention this more later on, but even if we have a choice, okay, why is dx preferable? All right, let's talk about that very quickly, and we'll reiterate this in 6.3 also. Okay, so why dx? Okay, why dx? Well, for one thing, you know, we want the disk method. All right. One thing we want the disk method. Okay, yeah. But what if we have a choice? Okay, even if we can choose between the disk method and the method we see in 6.3, which uses dy for this example. All right, even if we can choose, why is dx still a good choice, the one we'll tend to look at? Well, look here. We're given y as a function of x, right? We're given y equals x squared. We have y solved in terms of x. All right. Now, we can also solve for x in terms of y, but you know what? The square root we're going to get, we're not too keen on that. So we're hoping that, you know, by using the dx way, we can avoid square roots. Okay. Another reason, look at the region. The region is well suited to a dx scan. Because look at this thing. As the Xerox scanner goes like this, right? You agree there's consistency, right? The point on top is on the parabola, the point on the bottom is on the x-axis, right? That's consistent, all right? What if I do a dy scan? Okay, we look at the right point and the left point. What's a key problem with doing a dy scan? Okay, great. Go through this rectangle here, and then what happens? There's a change, isn't there? Okay, you agree. Here it's a rectangle, great. But over here, we have this line segment, fine. But then we change to the parabola. Okay? Now bear in mind, if you do it the dy way, you can get the right answer, but I think it's going to be more work. All right? So, aside from the fact that we're focusing on the disk method, there are two other reasons why we're inclined to choose a dx scan. For one thing, we have y in terms of x right off the bat, and if we try to solve for x, that doesn't look as good, right? Sometimes we can't do it like that. And also because the region there is better suited to a dx scan than a dy scan. If you do a dy scan, I'm pretty sure you're going to need two integrals, or at least an integral and some analysis. The fact that's a rectangle may be helpful. All right. Okay. Questions? We'll reiterate these themes. Okay. The method, the way the equation is solved, and the nature of the region. All right. Example. The region R is bounded by, okay, well, our old friend. I'm trying to get the principles across anyway. It's bounded by y equals x squared. Okay, of course you should know your pre-calc more extensively, you know, but bounded by the graphs of y equals x squared, y equals 1, and y equals 9. All right. R is revolved about the y-axis. I'll just write this. We're revolving the region about the y-axis. Okay, that tells us that. Okay. Find the volume of the corresponding solid. Okay. Now on the test, I'll write it more elegantly than this, but bottom line, that's what we're dealing with. Okay. This is elegant in its shortness. Right. Find the volume of the corresponding solid. All right. First of all, let's sketch the region. Oh, and you know, I was going to promise you I was going to give more points here. This is 0.11, this is 0.39. Bear in mind, if I ask you to sketch the region on the test, I may very well ask for the various points of intersection intersection, like the corner points of the region. Okay, so there's 1, 1, there's 3, 9. Again, in my notes, I may not do that as often as I should. All right. All right. Now, let's see. Okay. All right. So let's sketch the region, and by the way, let's find the corner points as well. All right. Sketch the region. All right. So R is bounded by the graphs of. Okay, so we have y equals x squared. That's this guy. He's our old friend. All right. We have. I'll label him for now. Y equals x squared. All right. We also have y equals 1. That's this guy here. Erase this piece. Okay, y equals 1. All right. And we have y equals 9 over here. Y equals 9. All right. So we have this guy here, and here's okay. So this is the guy we want to revolve about the y-axis. Okay. We want to revolve that around the y-axis. Okay. Now the thing is, though, I don't want to revolve that entire thing 360 degrees. Okay, because I'm kind of double counting, right? He's just swinging around. So actually, the region I want, okay, the region I want to revolve, okay, so we're going to have a new region, okay, the new R, okay, the new region, you agree that if I just take half of this, that's enough, right? Okay, I can ignore this part. If I focus on this half here, I'm good, right? The new R. All right, turns out we're going to want to dy scan of that. So you agree if I take that, sort of flipper, that fan there, all right, and I rotate it around 360 degrees, I'm going to get the full solid. Now in general, we don't like it when the axis of revolution goes through our region, but if you have a symmetry like this, then you can cut off the piece you really need, and that's okay. All right, so this is one of the rare cases where it's okay that the axis is going through the interior of the region, because we have a symmetry here that works. Bear in mind, in general, we're more nervous about that. All right. So that's our new R. Okay, that's what we actually want to revolve, right? That's right. Let's say that right now. Yeah.
You mean what in the last one, the axis was going through the region as well?
No, it wasn't. It was just grazing the edge. Remember? It was just grazing the edge.
Oh, okay.
This was going right through. And you agree, if I take this entire thing and revolve at 360 degrees, am I double counting? In a way, but and bear in mind, you know, the method we're going to use is not really well suited to that anyway. Yeah. Okay. So I don't want to think about, well, how's this thing double counting? Yeah. Just say, look, this is actually the region of revolution. Okay. If I revolve this fin 360, look like a shark fin. If I revolve it around 360 degrees, I'll get the whole thing. By the way, what does this thing look like? It's like a bowl of cereal filled in, right? Like a bowl of filled in cereal, right? Okay. Again, step 2 is usually optional, but you're going to get a bowl. Yeah. Except it's solid. Right. It's a solid bowl.
It could be a thin bowl filled with water.
What was that?
It could be a thin bowl filled with water.
All right. Very good. Okay. All right. Okay. Now here's the thing. If I tell you that I want you to use the disk method, all right. So let's see. All right. Maybe I should really number these, but okay. Let's talk about y dy. Y dy. Why am I suggesting a dy scale? Well, for one thing, if I tell you that you have to use the disk method, okay, then you must use dy. It must be dy. Okay, you have no choice there. If I say you must use the disk method, okay, then you must do a dy scan. You can't do a dx. All right? And why is that? Why is it that it has to be a dy scan? Well, because the axis of revolution is what? It's the y-axis. It's vertical, right? It could also be like x equals 2 or something, or x equals 10. Maybe x equals 10, right? Okay. Bear in mind, we don't want the axis to go straight through in an asymmetric sense. But because we have a vertical axis of revolution, all right, that means that in order to get disks, all right, then we need to have these toothpicks. Okay. I don't care how this way. All right. Again, if you're curious what happens if the toothpicks go this way, that's 6-3. We'll talk about that. But what happens if I take these toothpicks and revolve them? We get discs this way. In this case, thin discs.
When we answered the question why dx, and what was our answer? Was it this?
Well, for one thing, if I say you have to use the disc method, you don't have a choice. If it's a horizontal axis of revolution, you have to use dx or dt or whatever that horizontal variable is. If you're revolving, but let's assume for now we're doing it in the standard xy plane. If you're revolving about a vertical axis, it's got to, and I say you have to use the disc method, it must be dy. All right. Now, I mean, because this is the way you get discs, right? The hash marks are going this way. So that's why you want your hash marks to go like that, not like that.
Can we say that those toothpicks are parallel to the normals?
They're perpendicular to the axis. That's another way of looking at it. The toothpicks are perpendicular to the axis.
What about the normals? Like, would the
Is it normal?
Talking about the partitions.
Oh, you see this is like a partition maybe? Or?
that cursive P, that's.
Okay, yeah. Yeah, it is true that the underlying theory, you kind of think of rectangles, you relate to these slots here, right? Okay, then yeah, you have rectangles, the thick discs, right, and so forth. And the whole idea is that you're letting the norm approach 0, that means that we can use an integral. That means that eventually we're going to get an integral. That's what that says. The point I'm trying to make here is, why is it we're using a dy scan and not a dx scan? Again, if I force the disc method on you, it must be dy if you have a vertical axis of revolution. You have no choice. It's got to be dy. But another point I want to make, though, let's say you have a choice. Let's say I don't force the method on you. Okay? Why else? Okay? Why else might we want to use dy? All right? Now we have y equals x squared. All right? But y equals x squared, it's still pretty easy to solve for what? It's easy to solve for, x in terms of y. Okay, remember, you want to solve for things for the other variable in terms of the variable of integration, all right? Because remember, when we say we're going to solve for x in terms of y, that junk in terms of y, that's what's going to go in the integral. Okay, now, although right now it's y in terms of x, you agree, as I said before, okay, you can pretty easily solve this for x, right? If y is x squared, what is x? It's what? Yeah, we start with plus or minus root y. Because we're choosing this right fin, not the left fin, we're choosing the positive case. Although if you wanted to choose the negative case and take him instead, that's fine. There's nothing wrong with that, but obviously he's more natural, right? So look, x equals root y, which means that instead of y equals x squared, I'm going to, now this isn't wrong, but I'm going to think of this graph here as being a part of the graph of x equals root y. That's how I'm going to think about that graph. Okay, it's the graph of, it's a part of the graph of the equation x equals root y. That's how I'm going to think of it. All right. Bear in mind, these equations are equivalent if your x is not negative. Right. They're equivalent anyway.
If for some reason we did want to use a dx scan, could we use that y equals 9 as kind of like our base?
Okay, now if you do a dx scan, it turns out that 9 will not be used in computations. I want to postpone the dy. I want to postpone the other method for now. Because you know what? I think let's focus on this for now, because we don't want to mix too much right now. Later on we will.
Okay, so I'm kind of confused because for dx you said you don't want that part because you want to avoid square root.
Okay, now with one of the reasons why we want dx is because we have y in terms of x. Now you could say here, well, wait a minute. This guy is, we have this equation solved for y in terms of x. Okay, so you might say, well, isn't that an argument more for dx? I agree. But here's the thing. You agree, it's easy to solve for x in terms of y. It's not that bad. Okay, now we do pay a price. We have the square root, but we can do it. Okay, so you're right. I mean, you might think, you might think dx. Okay, would that be better? But, you know, it's also easy to solve for x, which means that we could go either way. It's not that bad to get this. We'd rather run with this, but you know what? If we had to, we can do this. We're not prevented from doing that.
Are you going to give us if it's going to be revolved around the y-axis?
I typically will give you what the axis is, unless I'm telling you, find the volume of a sphere or cone, for example, in which case you can model it on your own. It depends on your model. So don't talk about that. That's a good test.
So it's good to use dy with
Okay, so here's the train of thought. We have y equals x squared. Right now we have y in terms of x. That might suggest dx. But then wait a minute. You know, if it came down to it, we can solve for x in terms of y. So dy is okay. I'll put it this way. dy is okay. All right. The fact we can solve for x in terms of y. All right. Now bear in mind, if this were some ugly fourth degree thing and you can't solve for x, then you're pretty much stuck with that, with dx. Right. But come on, we can invert it. We can do it. Okay. Which means that if I tell you the disk method, then it's not so bad. We can do it.
So we use this method based on whatever the bounding graphs are. If it's y equals and as the
Now bear in mind,
constraints.
the disk method, the issue is the axis of revolution.
Yeah, I'm
Okay,
saying,
that's the key. Yeah.
is it easier to choose a axis revolution based on the restricting boundaries? Like for this example, it's
Okay.
restricting boundaries are y equals 1 and y equals
Well,
9.
no. Normally you don't have that choice. Normally you're told, hey, this is the axis of revolution. The only time you have a choice is like that. Those, find the volume of a cone or sphere where you model it. Those are very special cases. In a typical problem, I give you the axis.
Okay.
I mean, you agree that if you take this region, you're
Well,
going to get a
as
different
far as-
solid if you revolve around the y-axis as opposed to the x-axis. In fact, around the x-axis, you're going to have a gap. You're going to have like
Yeah,
a
so
hollow
it's
thing.
whatever axis
So I give you the
revolving
axis.
around is basically that's x or y. That's the type of
Yeah.
scheme.
So again, for this method, in a way, it's easy because if, for example, the x-axis is the axis of revolution, you know it's the x.
Yeah.
And you have to use it. If I tell you this method and the axis is the y-axis, it's dy. So in that sense, that's one reason this method's easier to remember. Well, we get x-axis, dx, y-axis, dy. But I want to show you why
have
that's
to even think about which one you choose.
no. But bear in mind, the point I'm making is, later on in the chapter, you'll have a choice. You could do it either the disk method and dx, maybe the other method we're going to see, and dy. And I'm arguing here, well, even if you had a choice, still, dy would be okay here. dy is okay because of this. The equation says we could do it. Now, here's the thing. The region, that's the real issue. The region is the big issue. More than anything else, the region is telling you. The region is telling you that we would tend to prefer dy. Okay, the region is really key here because look, dy. The point on the right is always on the parabola. The point on the left is always on the y-axis. What if I try to pull a dx stunt? Tell me, what's the problem if we try to pull a dx stunt here? We're going to have to use a couple integrals. It's going to change, right? Because top, line segment, great. Bottom, this line segment, great. We're great, and then from here, we're changing. Now it's still okay, right? It's not too bad, y equals x squared. But we're going to need, we need probably a couple integrals. Or at least some analysis and at least one integral.
You can break it down into two different sections.
Yeah, you can do it. Now, I'm not saying you can't do it the other way, but don't you think we tend to prefer one integral? Generally speaking, we would. We would generally tend to prefer one integral. Yeah. Not always, but generally. In general. All right. Questions? Okay. Now, bear in mind, if you have a choice, then maybe you could do it either way. It's just that one way might be better or easier. Right? In fact, there are a number of problems in the homework where I have you do both ways. Okay, you make your judgment. All right, well, I better keep this in there. Okay? So,
Well, wouldn't you only need one integral? If you broke that down into a rectangle and then solved from the rectangular piece over, you only.
that's what I mean. There are ways, well, that would be a cylinder, right? Okay,
Oh,
so you're right. Either two integrals or a separate analysis and one integral. Okay, and that might be okay. So I'm not saying that two integrals are always bad. Okay, but I'm just saying that generally speaking, we'll tend to avoid that. Okay, because a lot of people forget, okay, wait, let's do a cylinder. All right, I for h. All right. Third, let's find the area of a cross section. All right. So what is the area? Okay, of the cross section. CS, the area of the cross section at y, at some y value that's between 1 and 9. All right. So again, this will be helpful. So pick some random y value between 1 and 9. Bear in mind, if they ever meet, you don't want a dot, But and you might want to avoid the end values, right? But some nice representative value for y between 1 and 9. Draw the line segment. textbooks and instructors draw a full-blown rectangle, so you get some delta x thickness. But you know what? People have a hard enough time thinking with the thin slits. I mean, I don't even want to get to the rectangles. But I know a lot of books use rectangles, and then you have some thickness delta x. I think that confuses the heck out of people. So we're going to do the thin discs. Thin discs. We trust that the Riemann integration will work. All right, we take this thin disc, or we take this line segment, right? We revolve it, we're going to get our thin disc. All right. Now, what is this area going to be? Well, the area, okay, is going to be, you can think of this as A of y. You don't have to state that explicitly, but you can think of this as A of y. It's a function of y. Right? Okay, well, remind me, you have to know your basic geometry. What's the area of a disk?
Pi
Pi r squared. The area of a circle, I should say. Pi r squared. Pi radius squared. Okay, remember, later on, we're going to use r as a constant. So right now, I want to say pi times the radius squared. Technically, it's r of y. Technically, this is r of y. It's changing with y. So some people indicate that. All right. Okay. So what is the radius? Okay, so what is the radius? The radius is going to be, it's going to be the x-coordinate to the right minus the x-coordinate to the left, and these are in terms of y. Okay. So it's the x-coordinate on the right, okay, this guy's x, minus the x-coordinate on the left, and we want to write these in terms of y, because that's the stuff we're going to put in the integrand. Okay, I know you're going, okay, wait, we want the difference in the x-coordinates, but written in terms of y. Yeah, okay. All right, think of y as a fixed constant right now. Okay, think of y as a fixed constant. All right, well, what is, okay, given this y, what is the x-coordinate of this point in terms of y? Yeah, that's why we need to do that. Solve for x in terms of y. It's root y. Minus, what's the x-coordinate here? Zero. Right. Okay, if you're up against that axis, you're revolving about that coordinate axis, 0. All right, 1 is 0. All right, so we get root y. All right, and you can check, you agree that's non-negative on the interval, right? That's a check. For the test method, that's not so important. Okay, so root y. Okay, that's be the radius. So what's the area? The area is going to be pi times root y squared. Oh, I love this. You know, y is non-negative, of course. What's the square of the square root of y? Y. You get pi y. All right. In square meters, but that's not the point right now. Okay. Let's assume these are in meters. Okay. So for example, if I take this line segment, revolve it around, right? What's our area? It's 1 pi, right? Here. Over here, it's going to be 9 pi, right? Y is going to be 9 pi. That's going to be the area of that circle up there. You know, one side of the circle. Of course, we only count one side of the circle. The circular plate. All right. Questions?
Just, I mean, if you wanted to, you know, you're trying to figure out how to do a D-scan, a Y-scan, or an X.
Yeah, yes, do I have?
I mean, if you were doing a DX scan here, I mean, when you were doing your intervals, what do you call it, your integrals, your definite interval,
Yeah.
you wouldn't have your 2 points to go between. Like here you have 1 and 9 to go between. You don't have one to
Oh,
go
okay.
between.
Yeah. So what you're going to need is you're going to need to know what the x-coordinate of this point is, right? And by the way, even then, even if we're not going to that other method, reminding me, it's good to indicate where these points are. Okay. When y is 1, x is 1. When y is 9, x is 3, as it turns out. Okay. So I'm writing these numbers down here. I'm indicating what these coordinate points are. Okay. By the way, that comparison last year is a -1 here. Okay. But the thing is, if you do it the x way, you have to integrate from 0 to 1, or consider the cylinders. You integrate from 0 to 1, and then plus integral 1 to 3.
Yeah,
So
so
the
you're
bad
right.
news is you have two integrals.
Yeah.
Or you have to do a separate analysis and at least this one. Okay, it's doable, but I'm saying, you know, we want to choose a better method. If it's the test method, you're forced. Anything else? Anything else? Again, I don't want to talk too much about the other method just yet.
So any point on any of the x on the right will always be the plot. Yeah.
Yeah, the y can be any, you agree, y can be any guy between 1 and 9, this analysis will work. Now, of course, if your equation's changing, you might have to split the problem up, so you'll get a couple integrals or something, right? I mean, if all of a sudden you get a line here, then you got to split things up, right? But here, it's just a parabola, just this line segment. We're solve your equations. Yeah. So remember, you solve in terms of the variable of integration. That's always the case. You always solve in terms of the variable of integration in the 6-2 way or the 6-3 way. Either way. Right? Anything else? All right. The easiest part is the integration. See, that's the thing. That's why I don't mind on your chapter 6 test. A lot of your problems are setup problems. That's the hard part. I kind of assume you know how to integrate most of them, although I can ask you to go all the way. Some of them are tricky. But the key problem in chapter 6 is knowing how to set these up. Okay, they're kind of like word problems in that sense, knowing how to set up the thing. And then the actual computation is not that bad. All right, step 4. In fact, I'll just do it very quickly. Integral from, it's a dy scan. Now we're integrating from what to what, though? Integrating from 1 to 9. 1 to 9, right? Because remember, these coordinates correspond to that variable. Okay? Okay, 1 to 9, and we're integrating pi y. Okay, come on, pop out the y. Oh, sorry, pop out the pi. Pop out the pi. You can't pop out the y. Pop out the pi. Go on. You can do this. All right, you do this. Final answer is what? Hey, it's nice. Yeah, 45. Yeah, 45. And if the original distances are in meters, what's the unit here? Yeah, cubic meters per volume. Yeah. So that'll be our volume. 45 cubic meters. Very nice. And I have a generic picture in the notes. Again, I don't like fixating on the F and G notation because come on, you have to come into a basic geometry, draw things out, and be careful. Use your head, go step by step. So really, the formulas that you really need for chapter 6, you should already know. Really, the formulas you need for chapter 6, you should basically know.
For this example, say it's not symmetrical at all about the y-axis, how would you go about
Oh,
solving that?
well, yeah, here's the thing. I would not give you a problem like this, where if it's like this, I'm not going to give you this kind of problem. No. Well, actually, here's not so bad because, in a sense, you just take that piece, right? And then so, I'm not going to give you something like this, like that, where I'm not giving you something like that. So we can all right. If the axis, I'm making sure not something like that. Okay, okay. If the axis is going to the interior of the region, there's got to be some symmetry. Okay, there's probably I didn't care if am I drawing something bad here. Okay. All right. Okay. Any questions? Any questions? There are a couple ways we can extend this. For example, what if the region is not flush up against the axis? What if there's a gap in here? Okay, then we don't get actually a disk, we get something else. All right. So, where's this? What happens if there's a gap? All right. But it's really not too bad. You just adjust the formula. All right. Yeah. Okay. So I'll start with a generic picture here. So let's start with a generic picture. X-axis, y-axis. All right. Generic picture. Okay. So here we have y equals f of x. I just want to indicate we have y solved in terms of x. Down here we have y equals g of x. X equals a. X equals b. Of course, there are many cases. It looks like a Frito-Lay chip. Of course, there are many cases where you have to find intersection points, and the graphs actually meet. They taper off at the ends, and you have to find out what a and b are, or you're given one and you have to find the other. Okay, here I'm giving you a and b. All right. Here's the region you care about. All right. And we want to revolve about the x-axis. All right. Okay. Now, when we do that, all right, we're revolving around the x-axis. So again, we want to do a dx scan. Okay, we're going to do a dx scan. All right. So still in section 6.2, you have to do a dx scan if it's the x-axis. But this time, if we take an arbitrary x between a and b, I take this line segment. I know some books do a full-blown rectangle, but I mean people have trouble enough with a toothpick. All right, take that toothpick, kind of flying, and revolve them around. I don't get a circular disc. What do I get? Can you see what happens here? This point is going to sweep out this outer rim. Oh, wait a minute. What else do I have in here? This sweeps out a hole in here, right? If you have a gap, you're getting a hole, right? So, right? So what's this guy going to look like? Yeah, like a frisbee, right? And actually, now this word, you see this in construction. instructions sometimes, like if you put a screw in a screw, right? A washer. Okay, the washer method. Okay, the washer method. All right. So, and again, this comes from the Remont development. Bear in mind that this time instead of hockey pucks, we get hockey pucks with holes in them. All right. And in fact, these are the department's property. All right. Here's an example of a solid that's been decomposed into some washers. I'll pass these around. These have some thickness, delta X, right? I'll pass these around. Don't play frisbee with each other. Okay? I want to see a frisbee one. Don't play with these washers. All right. All right. But now here's the thing. How do I find this? What is the area of this, though? All right. Well, you're going to need two parameters. You're going to need this outer radius. I'll call this R sub out. Okay. You're going to need an inner radius, R sub in. Okay. So the radius of the outer rim and the radius of this hole inside here. Okay. So what is the cross-sectional area then? All right. The cross-sectional area here is given by. All right. What's the area inside the big circle? Pi r out squared. What are we gonna do?
Minus.
We're gonna subtract the area of the hole. What's the area of the hole? Pi r in squared. So in a way, it's the area of the hole, W-H-O-L-E, minus the area of the hole, H-O-L-E. All right, it's the big area minus the small area. Big area minus small area. Right? Big area. Of course, this is not negative. Big area minus small area. All right, and this will always be non-negative. Area. Okay, we're not signing things. All right. So that's the key adjustment. Okay. Otherwise, okay, we're good to go. All right. Although here it might be trickier to find out what A and B are, right? Because here it might be a bit harder to find intersection points. Okay. Oh, and by the way, so what's the volume formula going to be? Here's the overall structure of the volume formula. All right. So the volume formula is going to be integral from A to B. Pi r out square minus pi r in square. Bear in mind these are functions of x. These are functions of x, right? Dx. Or if these are functions of y, we have dy. That's going the other way. All right. So pi r out square minus pi r in square. Well, those guys are functions. They're changing with x in this case. All right. Dx. Okay. And then if you do it the other way, right, if you have like you're revolving about the y-axis, right, you have these two picks over here, all right, then here the volume will be very similar, except you're going to have functions of y and then dy. The theory is exactly analogous, right? I mean, the theory of calculus doesn't care if it's dx or dy. As students you do, because you have to draw things and write equations. But the theory of calculus doesn't care. dx, dy, same theory. Same theory. Get over the issue of letters. It's the same theory. Who cares if dt, beta, whatever. Okay, so the shift in letters, that should not even bother us. Although graphing, that does have implications. All right. Let's do examples. And obviously you're going to want to do this by doing examples.
This, with the revolution symbol with the 3 lines.
Well, I'm going to do some sample toothpicks.
Oh,
Like here. Here's the toothpicks are vertical, right? So dx scan. Here the toothpicks are horizontal. Y scan. I just want to show that it might not be dx, it might be dy. I just want to make that point. It might be dy instead of dx. In which case, this stuff is in y. Let's do the example. You got to do it. You have to be a real genius to just get it from the pure theory. Well, do examples. Work it out. Right? Example number 14 in Sokowski. All right. R is bounded by. Finally, not a parabola. R is bounded by the graphs of x equals y squared. Sorry, y cubed. X equals y cubed, and x squared plus y equals 0. X squared plus y equals 0. We're going to revolve around the x-axis. Okay. Find V. Find the volume of the resulting solid that's generated. Okay. Now, solution. All right. Now, bottom line, we're going to use the Washer method. Okay. Let's say I tell you that you use the Washer method. Okay. I tell you, you must use the Washer method on this problem. sometimes I do like to force it so that I know that you know what to do using a certain method. Okay, now if you use the washer method, okay, then hey, again we're revolving about a horizontal axis. That means we're going to need a dx scan. All right, if you're revolving about a horizontal axis, okay, just like for this, the washer method would want the dx scan. So remember, folks, the disk and washer methods. You know, the washer method is really just a generalization of the disk method. Or in other words, the disk method is a special case of the washer method, where Rn is always what on the interval? Zero, where there's no gap. Or Rn is always zero, there's no gap. Okay, so again, just like with Rawl and MVT, right? The disk method is the special case of the washer method, where basically Rn is zero, there's no gap. Okay. Still, the dx dy issue, that stays the same, right? If you have a horizontal axis, it's dx. Okay, so in that sense, it's easy to know which guy you pick if I force disk or washer one. All right. Let's sketch the region. All right. Or let's consider the region. All right. Let's sketch the region, and we'll consider its properties. Okay. Now, first of all, we have a bunch of things that get wrapped in here. So I'm kind of combining a bunch of steps from 6.1 because I'm doing it all in here. All right. Now it's a dx scan, right? Which means that I have to write the equations. How? I have to write them, well, for y in terms of x. So y equals a function of x, right? I want to write these equations out as y equals a function of x. All right. In fact, sometimes it's not even a function, in which case you tear it apart, plus minus. All right. Take a look at these guys. X equals y cubed. That was kind of a trick. Okay. And that's why I didn't want to delve too much into which approach do we use, because let's say I start with the washer method. All right. We have x equals y squared. Now that would tend to suggest a dy method, but wait a minute. If I say washer method, you don't have a choice. It's got to be dx. But don't you agree? I can solve this for y pretty easily, right? If x is y cubed, what's y? The cube root of x. Straightforward. Y equals the cube root of x. All right? Let's look at the second equation. X squared plus y equals 0. Now this guy, naturally, you'd want to solve for y in terms of x anyway, because we like to avoid a square root. Okay, so the first equation, he's not too bad. We can write this out. Second guy, if anything, we'd rather solve it for y. Y equals, be careful,
Y that negative x.
opposite of x squared, yeah. Don't forget that. All right, so we've rewritten the equations for y in terms of x, because the washer method and this axis says we have to use dx. You don't have a choice here. Okay. If you do have a choice, you know, right now it's kind of a tie. We might want to look at the region, right? Okay. I think the other method is fine here too, actually. Okay, now, wait a minute. Where are A and B? I think I'm gonna have to locate what points? The intersection points, right? The intersection points. All right, because intersection points tend to naturally cross each other, right? Okay, so let's find intersection points. To find intersection points, that usually means I'm solving a what? A group of equations called a system. Solve a system. Okay, so let's solve this system. How do you find the intersection point between two graphs? You find the solutions to the system containing the equations for those graphs. Okay, so I care about these two guys here in particular. All right. Notice here, there's no mention of the x or y axis being a boundary. Okay. Yes, for revolution, but not as a boundary. So I just care about these guys for A and B. All right. Sometimes the x or y axis might be a boundary, not necessarily here. Okay. All right. Let's solve the system. So we have, well, you know, it's convenient we've already solved for y in terms of x. That's kind of natural for the substitution method. Y equals opposite of x squared. Okay. Well, for any intersection point, any point has only one y coordinate, right? So, you know, if this guy is that, it's also got to be that. All right. So we set the y's equal to each other. We get the cube root of x equals the opposite of x squared. All right. So I set these two expressions for y equal to each other. Because, of course, a point only has one y coordinate. All right. Now, I'd like to get rid of this cube root. Okay, this is very clean because it's one-to-one. What does doing a cube root? Cubing. Let's cube both sides. What's the cube of the cube root of x? It is x, that's clean. Alright. The cube of negative x squared. The cube of negative 1 is negative 1. What's the cube of x squared? X to the what? 6. Okay. Yeah, that doesn't matter so much, but yeah, x to the 6. Alright, x equals negative x to the 6th. Do you want to divide by x? I would say avoid that. Okay, because if you do, you have to consider the special case. Because you'd be losing 0.